name and Petraco is in the error message, that probably means that there's a path someplace that needs to be changed to whatever the path is on your computer. The two first places to look are at the top of any actual computation script like this, where I put the word source. Source means how you load the information into the R framework. So anytime you source a file in R, it goes through that entire file and loads everything in there into memory. Typically, you will just source files that are full of functions. In other words, things that don't necessarily execute right away, but you want them to be able to execute when you send data into them. So in order to get this to run as fast, as up and running as quickly as possible, I did it quick and dirty, and I just sourced a bunch of function files. So the path to those function files has to be correct for your computer. And I don't really know any easier way to do this other than write a package for you. But then that presents a bunch of other problems. So this is, if you know what a path is and you can change the path to your computer, especially if you're having trouble and I'm around, I can help you figure it out. Also, wherever you come from, if anybody knows anything about computing or playing with these kinds of things, they'll probably be able to help you as well. So anyway, the first place to look, usually if you have an issue, is the path at the top of the computation files, because that has to be changed to your computer specifically. The SourceMe file is what you want the path to. The SourceMe file is basically the file that sources all the function files that I have written. Let me show you what that file looks like, because there's actually one thing in there that you should change as well. Everybody ready? I'm just going to minimize this for a second. Within the R file in your little distribution, you have another file called rsurfmetdemo. That's where I dumped all the function files. You see this function, you see digitalsurf.r, that's where the code is to open up the digital surf files. If you want to open it up and see what I do, it's right in there. Here is the SourceMe file. So if you click on this and open it up into R, let me just pull it up. So within the SourceMe file, you have another path that you definitely have to change, because this is hardwired for my computer. So in the SourceMe, where it says SourceMe root D, that string needs to be to wherever you have the rsurfmetdemo file. Because basically what this file is going to, what this SourceMe thing is going to do, when you source or when you load the SourceMe file, what R does is it opens this thing up and goes and executes all of these. The first thing it does is it actually loads this RGL. We'll talk about this in just a second. It loads this RGL library. On your computer, you might have to install packages RGL. Well, in fact, if you do this for the first time, you'll install packages RGL. If you do that caret thing that I tell you to do in the abstract, you guys remember you may or may not have seen the abstract for this. On the abstract, I tell you, you should go and download and install caret with all the depends.
Install that, the base, install Studio.
Yeah.
And install some stuff, but not the one that was going to take forever.
Yeah. But if you do that, this package gets installed in the process. And actually, I'll tell you what this is. You know OpenGL?
Yes.
OpenGL is a great but very low-level, three-dimensional interactive C-like language that plays nicely with GPUs. This is the package that R uses to talk to OpenGL. And if you load this package in, you can do three-dimensional interactive plots, which actually we'll do. We'll see some of them. If you try to execute this script and you don't have that loaded, or if this isn't on your computer, installed on the computer, you'll get an error. So you should do an install packages. But if you do everything I tell you to do in the abstract, you should be fine, as long as you change this path. Change this path to wherever this file is on your computer. Okay. Yes, another thing. Sorry. Watch out for on Windows too. On Windows, the file separators aren't /. This is really annoying. I'm sorry I didn't mention this before. You need 2 double backslashes. So if this was Windows, I would say something like C:\\\. Let's say it was in the user's file.
Windows 7.
Oh, they changed it?
7 is fine.
Okay. If you run into problems and it still gives you errors, Google, the first thing I would do is Google the error message and say, okay, are having problems loading, and then Google that whatever the error message is. And then some nerd somewhere will have written on one of the user sites how to fix it. Or somebody will complain about the same problem. 99.9% of the problems I've had with this program, when I Google my question or something closely related to it, I find somebody else who's had a very similar problem and a fix to it. Again, it's not the greatest thing in the world because you really, I like instantaneous gratification. But if you can get around that, almost always you'll be able to find a fix on the web. And mostly it just comes down to just having fix a space or something like that, or put in an extra slash, or you need single quotes instead of double quotes. So it's something usually pretty simple. So when you open this up, that will load. This string will get saved, and then R will go through here, and it will basically, it takes the root directory string and it pastes it onto whatever I call the function. So this paste command basically just pastes a giant string together, which points at that file, and it sources it. So this is the easiest solution I've been able to think of in the couple of years I've been using this to get people up and running quickly with this program. But it is frustrating, and it probably won't work the first time. Feel free to email me at any point, although I am very slow on email, mostly because I have students or somebody else or my wife screaming at me to do something else. The more you nag me, the more likely it is that I will answer you. And you have my undivided attention right now, so I'm happy to help anybody I can if you want to get started with this program. I don't want you to get frustrated while I'm here. So if you do those fixes, make sure that's installed by following all the instructions in the abstract, or just doing install packages quotes RGL, and fix that path. Hopefully, when you run in the demo.r script, when you run this line, you should get, oops, what did I do?
You selected the...
Oh, duh, yeah. Okay, yeah, we should. Yeah, if anything like this happens,
watch which window you're in.
Yeah, it's waiting for more input, and I just screwed something up. So usually if you just close parentheses, it'll throw an error for you, and you'll be done. You'll get your command line back. So that's what I'm going to try, and let's see if it works. So I'm going to close parenthesis. Oh, it didn't work. That is really annoying. Control C. Wow. Boy, talk about a mess. Let me try this.
Can you Control C out?
Sometimes you can.
Close quote.
Oh, close quote. Oh, there it goes. Okay, well, I'm out. Yeah, yeah, that's fine. So I just threw an error. That's fine. Nothing really got loaded. Now let me try to do it properly. So as long as the cursor is on the line someplace when I execute that line, yeah, I got no output. That's what I'm supposed to get. Usually either you want no output or a picture or a number, and that's good. When it starts throwing a lot of white text at you, then that means there was an error someplace, like something that looks like this. Look around for, don't be scared of the error messages either. Usually they're fairly informative. Read them, and you'll usually be able to fix your problem. And the reason why I say that is quite often I get really frustrated when the error messages come out. I'm like, what's going on with this thing? And as soon as I calm down and read the error message, it's a straightforward fix. And if I have trouble, I will often Google the error message and see what comes up. But with enough practice, it becomes a lot easier to use. Again, the learning curve is high, but it becomes more straightforward to use. Okay. So what I'm going to do here, I have two options for you in this demo.r script. If you executed this line, what this will do is it'll bring up a file chooser GUI. You can pick the file that you want to open up, and what this actually returns is just a string which represents the path to the file, which then you can pass to the read digital serve file function that I wrote. So this doesn't come with R. You have that on your thumb drive, and then the information will get dumped into here. Usually, though, I don't use this thing. I just wanted it in the scripts for you if you ever were curious. One of my graduate students found it. It's like, oh, Nick, what are you doing it this way for? Do it this way. And that's what he likes GUIs. Most of the time, I have my file source sitting in the same place on the computer all the time. So I just have the string to wherever the file is. So the file that we are going to open up is screwdriver 9A, replicate 4. It's a waviness file, but it's in .sur format. And this was literally taken as a picture on our Zeiss scope. I did the form removal and the waviness filtering in mountains, and then I just saved it as a .sur form. I saved surface in mountains. Now I'm going to open it up into R. You ought to be able to do the same thing with that little set of programs that I gave you. So I'm not going to use the chooser. I'm just going to use this. If you just use this, you don't need to execute the chooser as well. I just save that. I'm going to open everything up. Sometimes it depends on your computer. Sometimes it hangs for a second or two. It's not a tough operation for the computer to program, but it depends. I've run it on other computers and it runs instantaneously. On my little Mac here, it takes a second. But it's open now. If you want to plot the surface, you could do that here. It doesn't come out looking very nice. I just wrote this function, and it's really not tuned very well. And Mountains or ImageJ or any other bunch of really good surface metrology programs like Taylor Surf, and there's another one written by a guy in Pennsylvania. I know it, it's just losing me. I'm forgetting it right now. At any rate, they do a much better job at visualization than I do. I'm not trying to be a visualization program. I'm just trying to be a number crunching program. You can get things to work faster by, if you look at the code for this, what these represent are how many points you're throwing. I'm taking 256 rows and 250 columns. If I tried to plot the whole thing at once, it'll take forever. I highly recommend don't bother to use this. I put it in there so you can see what it does, but either leave it alone, play around with it a little bit. You may slow down may slow down the program a lot, but I would say don't use this for visualizing toolmark surfaces or any kind of surfaces very much. It's not fast at all. And it's a little tricky to use because you have to play with these numbers to get it to run fast. This is okay though, plot profile. Basically, if you tell it what profile you want, in other words, what row in the matrix you want, it'll plot the profile for you. So let's do that. Oops, figure margin's too large. Why is that? Oh, I know why, because I had the window all squished. It threw an error because it can't see the plot window. This normally doesn't happen, but my resolution's all screwed up. So if we plot the profile, oops, oh, that's terrible. Okay, here, let's do, here we go, there. I just made the profile there. So this is one of the profiles in that striation pattern that we have. In fact, let me show you what the pattern looks like. Let's see if this works. Okay. So there's my striation pattern. You can see things get pretty pixelated a lot. Maybe you can make this better, but again, there's better things around, so I'm not going to even try. But this is what the striation pattern looks like, coded by how high the surface is in Z, which you can kind of see over here. This part I did not write. Somebody in France wrote it, and I asked his permission to use it, and he never got back to me. I'm going to change it now. I'm starting not to like it anymore because it cuts off the ends over here when I make PDFs out of it. You can write a scale that tells you how high each of these are. Quick and dirty, I just put that guy's code in. And actually, I'm going to get rid of it. I don't like it that much. But just so you know what you're looking at, this is color. The surface is not actually green. It's just color coded by height, in case you're curious. And this is not a great function anyway. I just wrote it to be quick and dirty. What's better are the actual profiles. So profile along that surface, in fact, number 3 is what we saw before. And if you plotted up something like that, and you want to put a mean line through it, you can. I know a lot of people in surface metrology like to see where their mean lines are. So you can center it. There's an option to center it, and you can center things if you want, and you can even put the little mean line in there so you can see where it is. And most of the time, again, I don't use this kind of thing in research. If I need a quick and dirty visualization, I'll do it in this program. Now, remember how I was telling you that when I ran read digital surf file, it dumped a bunch of information into surface.info, which is a list of lists. So this is a code that I had in the talk in order to produce what's actually in there. So this will just tell you what the names of the 2 lists are. This one is going to grab the first list, and because I know that it is a list, and I know I have each of the elements of that list named, this will tell me what each of those elements are. So just to show you, so Oops. So the first, it just brought up the command line here. The first is surface info and surface, and then the more important thing is, where'd it go? Yeah. Let me make that bigger. These are all the different elements in that header file, and again, they're written pretty much with whatever the documentation for the digital surf was. The most important ones to us are typically the z increment, the x, y, and z increments. In other words, how far apart the points are in space and what I need to do in order to scale them from whatever integers the scope recorded with the detector to physical z height values. And whatever they are here are, you can say now z inc and it will spit out that number at you. And it also has units and stuff like that in there. Do you look like it?
Yeah, I'm just curious if you wanted to find the value in one of those.
Yep, I'll show you. Next line. Oh, it's not the next line. Well, it's kind of next line. Okay. This is how I should have actually made this separate. If you want to make a note of this, I would write, there's a couple ways to do it. It's kind of like a train. I'm going to take surface info, list 1, I want the x inc element. I could, whatever x inc is, it might be like the 16th element or something like that. I could type in 16 here too and it would do the same thing. I'd like to use the names instead. So if it's quotes x inc, it should spit it out. Let me take this piece of code out and I'm going to just put it, I'm going to separate it so you can kind of see it a little bit better. Copy. Just paste. Okay. So I am taking that header information and I'm going to grab the x inc element to be the, which is the distance between the points on the x-axis. If I execute that, I should get a number. Oops, yes, an ID. Hopefully, if you guys are doing this on your computer, it looks a little nicer. So here it is. And that's what its value is. If you looked it up, it's in units of millimeters, which is also recorded in the header as well. Now, when it gets spit out, in order to actually use it as a number, I had to do a little bit. This I did not know. I had to play with it a little bit. In order to actually use this 0.0001 value, I had to wrap it inside as numeric. In other words, I had to change the type. When, for whatever reason, usually it's not this bad, but again, it's not a WYSIWYG program. You have to fiddle with it a little bit sometimes. That's why it's good to go step by step. When I spit this number out, I tried to multiply it by another number, and it was giving me an error. And I looked at what type it was, in other words, what class it was, and it was saying it was a list. And I was like, why is it saying it's a list? It's saying it's a list because I accessed it from a list. And it's, again, it's like one of these little quirks that you trip across sometimes. So in order to force it to recognize that as a number, I put it inside the asNumeric function, which will do that. It'll get rid of all other attributes other than the fact that it's a number. And then because I wanted to use it for something later on, I save it in a variable called dx. That's what's going on there. This is a little bit more advanced, and I didn't plan on talking about this too much, but I haven't run into this kind of problem that I'm describing right now too often. It was just one of these little annoying quirks that I ran into as I was putting this little demo together. Like, why the hell is this not working? So that's what ended up happening. I calculated these two numbers because later on one of the R parameters that we calculate required them, so that's why I pulled them out. But that's how you access the values, and to make sure if one of them is like a Z, some kind of number, in order to make sure that R is recognizing it as a number, not a list, because I pulled it out of a list, you can wrap it inside the asNumeric function, and it will force it to say, oh yeah, this is a number. Sorry about that. Okay. Some of the other stuff that this little demo script will do is I don't use parameters a lot, and I'll show you why in the course of doing the rest of the statistics. But some of the things that we have hard-coded, because people have been asking for them, and I really should do a study of just trying to see how good discrimination works based on the parameters that we calculate off the surface. We just hack these up real quick, the real basic profile parameters. What we have to get to are the surface parameters as well. Whatever mountains can do, I want to be able to do as well. But again, it's kind of in low priority because we did a quick, when we first started this project maybe about 2 years ago, we dumped a bunch of parameters out of mountains, and we just did a quick and dirty discrimination, treating the parameter vector for each surface as a feature vector, and we didn't get great discrimination. And it kind of made sense because if that worked, everybody would be doing it. And if you look around for papers where people try to do surface discrimination based on the function, the metrological parameters, you don't find them. There's like 3 papers. And I kind of know why now, because it doesn't work very well. And if you look at the equations, like RA, that equation for RA, which is a mean, looks an awful lot like the equation for, it's very close to the equation for RQ, in other words, the standard deviation. And if you plot the two against each other, you see a tremendous amount of dependence. In other words, as RA increases, RQ is increasing. So the extra parameters, because their equations are so closely related, aren't giving you very much extra information on which you could do discrimination. So we haven't found, again, in our quick studies that we did, we haven't found very good discrimination just using surface parameters alone. That doesn't mean that there aren't some out there or that people couldn't do it more carefully and get better results than we did. We just found that early on we weren't getting good discrimination, and coupled with the fact that you don't see a lot of people in the literature doing this, it's probably a low probability of success if you approach the problem, the surface discrimination problem that way. You might be able to tell the difference between different milling processes or different kinds of machining processes of your surface based on the surface parameters. I think that's really what they're for. But will I be able to tell you which CNC machine milled that surface? Not with the parameters. I don't think so. No. With our techniques, as long as you do all the extra computationally intensive surface registration, I probably can tell you which CNC machine made those marks. But from the parameters alone, nah, I don't think so. But try it. Maybe I'm wrong. You know. At any rate, we hard-coded a couple of these because I would like to, especially because the engineers are so interested in them, they really should be a part of any program that we ultimately distribute to people. But they've been kind of low priority because we haven't found them very useful for our needs. There's a couple in there, though.
And these parameters, they include no filtering, though. They're just taking... No,
I did. I filtered the surface first, and I took the profiles and just dumped them through. So I did. These are real quick and dirty, not properly ISO standardized the way of doing it or anything. I looked in Roger's book and said, "Oh, that's what the equation is." Yep. There it is. Okay. I would trust the digital surf values much more than anything that we have put out with these parameters. But we only we coded those ones, and that's it so far. In a couple of years, we'll probably put them all in, but right for now, that's all we got. Okay. That's pretty much it for the demo. No, I don't want to save that. That's it for the demo script. There are 2 other scripts in there that you can play around with. I'm just going to talk about them briefly, and then we're going to get back to notes. Then we'll talk about these again at the end of the talk. But there's also a parameter analysis. So we took a bunch of the, I believe it was primer shear profiles. Just ran them through mountains and grabbed as many parameters as we could for them. And put them into that spreadsheet, and we tried to do the discrimination on the spreadsheet. We actually got decent discrimination. We got about, it depends, but we usually get about 88% correct, which isn't bad, but we only had basically 5 different guns in there. And on top of that, we need to get much better discrimination than 88% of the time we get the right gun. With our profile, like using the raw surface itself and lining everything up, we get 100% easy on this set, whereas with the parameters we were only getting 88. So that told us right away that the parameters aren't going to probably be great. But it's all reproduced for you here if you want to be able to look at it. And also the reason why I included the parameter stuff is it does the 3D plotting for you. So let me show you what that looks like so you know what the program is capable of. If you were to load in all those parameters and do 3D PCA on it to take, I think, well, I'll tell you in a minute. I think, let's do dim x. Oops, wrong button. Oh, I still did it. Do not compute in public. 18 parameters, so 70 rows, 18 parameters. So 70 different surfaces, we calculated 18 parameters for them. I'll tell you right now, there were 5 guns in those 70 surfaces. My space, if I was to plot it, is 18 dimensional. I can't look at that, but I can use PCA in order to boil it down to the most essential, according to PCA, 3. So just looking at that, really all I want to do right now is just show you a 3D plot of the data. That, and then we're going to come back to this, don't worry, I'm going fast. Okay, so this is R talking to OpenGL, and it will plot data for you in 3 dimensions, and you can turn around in space and look at it. Each of those points represents a different set of those 18 parameters, but throwing away a lot of information so I can plot it in 3D space. That's what PCA does for you. So that's actually what we're going to talk about. This is a nice segue into the next part of the talk, where we get into the actual statistics now. So what we have at this point is we're able to get, we know what R is, we know where to find it, we know how to get data into it. If we want parameter data, we can put it into spreadsheets and load it in. If we want actual surface data, you can use that digital surf thing that I wrote for you. Now let's get into some of the actual multivariate analysis that we use here. And I'm going to tell you why I use multivariate analysis as opposed to univariate analysis. And isn't that pretty? When I saw this, I was like, ooh, wow, look at what it can do. Okay. So we'll come back to the script and we'll play with it a little bit more, but let's get a little statistics into us first. There's one other script in there that's, what is it? Oh, profile, oh, visualize, yeah, some of the visualization stuff, like some of the graphing you can do with this, with the visualize with plots thing, and that shows you how to make the basic XY plots. We'll see them right now. Right, PowerPoint. Okay, I'm going to skip over this. We were talking a little bit about what the function should look like as for RQ. In other words, if you were to type in the RQ function yourself, this is sort of what the code could look like. I'll let you read that yourself. If you want to literally copy and paste this, it should work fine. But this is really just trying to describe to you if you wanted to write a function for yourself. And since it's a metrology course, I did RQ. This is what the function would look like, and this is ultimately how I executed it. After I had some surface data, I grabbed the profile and I calculated the RQ, and I got a number. So I'm going to skip over this and move on to the next thing. And I'm going to talk a little bit more about, get away from R for a second and show you what we have used R to do. One of the things that is common statistical practice right now in tool-marked discrimination in forensic science is to take 2 striation pattern profiles, because you get striation patterns not only on scrapes of like screwdrivers but on bullets. When you put bullets through barrels, they go through the lands and grooves, and in the land engraved areas you get these nice striation patterns, which a system called the Integrated Ballistics Identification System, which is kind of the benchmark system to use for bullet discrimination between guns, that uses images of the striation patterns in order to try to match up a gun with a particular bullet. The way that it basically works, it is proprietary, but people know basically how it works, is it calculates a correlation function on the striation pattern it gets off of bullets fired through a gun that they have in evidence, or bullets found at a particular crime scene, and the striation pattern on bullets found with the suspect or at a crime scene. In other words, they have 2 sources, and they can compare the 2 with a cross-correlate, a CCF function that is commonly used in statistical signal processing. Basically, they take these 2 striation patterns, which boil down to profiles. They can move them over each other, see which lag gives them the highest correlation value, whatever number that is. That's its similarity score. So that's usually how it's done, even in these 3D systems where they're trying to figure out how close 2 bullets are. Could they have been fired from the same gun? They calculate a cross-correlation value. And NIST is really into doing this right now. I like a lot of the things that NIST is doing, not that though. I don't think that's ultimately going to be the best way to go about doing tool mark discrimination based on calculating this one cross-correlation value. As soon as these data sets get bigger and bigger and bigger, they're going to get all sorts of overlap between their cross-correlation histograms, unless they do really crazy and things to filter out noise out of their surface profiles. And you're never going to be able to do that in a production level system. You just have to do too much work on the surfaces. When we take that idea, though, what is commonly used in practice to calculate these cross-correlation functions in order to gauge the similarity between two surface profiles out of our database without doing a lot of surface cleanup, which is what you probably end up doing in practice, this is what we get. So in order to do this, we did it on as big a data set as we could get, which meant we had to simulate some things. So we took what we had in the database and we simulated some more with a wavelet expansion, which I'll talk about if anybody's interested in. So that's what the wavelet, so we would feed in some real profiles and we use a simulation based on a wavelet expansion of the signal, and we'd be able to simulate more. So these are real, and this is what we got out of the simulator. So we had a good, we're writing a paper on this now to say, we think this is something legitimate to do. Anyway, I know it's legitimate, so we just built up the data set, ran it through the cross-correlation function, and we get a pretty yucky looking overlap between cross-correlation scores for known non-matches and known matches. In other words, if we got really good discrimination with just this number, without having to do a lot of extra work on the surface striation patterns, we would want this histogram to be way down there, the pink one, and we want this green histogram to be way over there and with very little overlap in between. And this is a fairly large size data set. In order to do this, we had, I think, about 200 real surface profiles, and then we built it up to about 1,000 real and simulated profiles. And we get pretty nasty overlap. Not bad, but not the kind of thing I would want to see in an operational forensic instrument. And if you look at the ROC curve, we want the ROC curve to be all the way up here, and we're not getting that. So we want really good recall and precision, and we're not getting that. We're getting a high error rate because, or unacceptably, I feel, high error rate because these two different histograms overlap a lot. And that makes sense to me because we're basically trying to do discrimination of two tool marks that contain a lot of information based on one number. We're taking a ton of information and we're boiling it down into one number. It's an information compression problem, and anytime you do this kind of information compression, you're probably going to lose so much information that you actually lose discriminatory information. This method works great on medium-sized data sets, but as soon as you start to get the big data sets, these histograms start growing into each other and you get lousy discrimination. So this is something that we kind of want to stay away from.
This data set is all matching one candidate to...
Yeah, we have a lot of guns.
Yeah.
We take a profile off of a tool mark from each, let's say, cartridge case fired out of each gun. So we have a couple of cartridge cases fired out of each gun. Each cartridge case corresponds to a profile, a mean profile. We take two profiles, run them through CCF, and we say, yes, it's a match, or no, it's not a match based on their cross-correlation score. I know the real answer, the computer does not. What we want to see is we get low cross-correlation values between known non-matches. Again, the computer doesn't know that they're not a match, but I do. So we want to see low cross-correlation scores between known non-matches, and we want to see high, very high cross-correlation scores between known matches. And most of the time we get that. I can see that there's two histograms here. However, there's a lot of overlap between the two of them. In fact, they overlap sometime around 0.6 or so. And cross-correlation is on, basically, it's on -1 to 1, but you never get -1. So it's on basically 0 to 1. That means there's a lot of patterns that, might even fool, they definitely fool a computer. They might even fool a human with the amount of processing that we have done. Again, this is really not to compare to a human being, because a human being is looking at something different than the computer is. But I don't want my two histograms this close. It really shouldn't be in the production level system. Now granted, I didn't cheat, but I didn't also clean up my surfaces a lot. If you clean up your surfaces a lot and get rid of like things that look noisy to a human being, you'll be able to get better separation. But again, that's a lot of computation to do for a production level system if you have many, 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 maybe even millions of profiles to go through. I don't think that's going to work for a production level system. I would fund the research, but do I think that's the future? No, I don't think so. And it boils down in my head to me taking a ton of information and compressing it down into one number, and I'm losing a lot of discriminatory information doing that. I think we should discriminate not based on one number, but based on as many as we can get away with, that also give you discriminatory information. In other words, information that tells me that this profile belongs to this gun and this profile belongs to that gun. Yep.
So if I may attempt to make an analogy, right? It's like you have data set 1 comprises the numbers 1, 2, and 3. I hope I'm doing this correctly. And data set comprises the number 2, 2, and 2. Okay. And I'm doing my mental math, and I'm saying, because we're trying to have a computer do this, the computer is going to take the average of the data set as the discrimination function.
Yeah, kind of.
So data set 1 contains the numbers 1, 2, and 3. Average is equal to 2.
Yeah. I like that analogy. I'm going to steal that from you. That's good. Yes, exactly.
3 for your use, no pay needed.
Okay.
And data set number 2 comprises 2, 2, and 2. Computer says average 2.
They're the same.
It's a match.
Yeah.
Okay. But if data set number 3 was 1, 4, and oh God, pick a number so that I can add it all up in my head. 1, 4, and 1, average is equal to 3, that is not a match.
Yeah, that's kind of exactly, that's a great analogy for what I think is, exactly what's going on, yes. And on top of that too, everybody is sort of approaching the problem this way, and I don't think I could add too much to it because I mean basically you're just using a really simple function. The hard part about this is the filtering.
A single parameter. So a cross correlation is not a single parameter. It's some.
Yeah, it's a composite of things, but it's still I don't find this particularly satisfying, and I can see big problems down the road unless you do a lot of work filtering out the surface. Then you get into arguments with people, and believe me, I'm married to a lawyer. They love to argue. You're going to get into all sorts of problems with people about how you're filtering the surfaces and how you're changing the data sets and whether or not that's something that you want to be doing to put somebody in prison for 50 years or worse yet, send them to the electric chair or whatever they do to kill people nowadays.
And they want to turn it all into a computer recipe because they don't want to have a person intervening in the filtering.
That is the opinion of some people, yes. I don't see it happening that way. All I see happening is that the computer recipe will aid the human being. I don't think we're nearly to the point in AI that the computer will be able, not even close. And I'm not saying this because I have a lot of friends who are in tool mark analysis. I'm saying this because I totally believe it. We are not to the point in artificial intelligence where a computer can make a reliable decision on a problem this nuanced. Okay. No way. And it's definitely, my personal feeling about it is definitely it's not the right road to go down to go take this approach.
So you might be able to use a computer to match paint colors for painting the wall.
It will, yes, that or it will help you. You need some way to cross-check it against a human. Like what I teach my students all the time, whenever you use a calculator to calculate anything, and they're ubiquitous now, so I don't accept that you're not supposed to use calculators for things. We do. But don't just believe the number that gets spit out of the calculator.
You still have to do it by hand.
Well, okay.
Yeah.
Don't just believe, even if you do it by hand, don't just believe whatever gets spit out at you. Think about what it physically means. Does this make any kind of sense at all? So even if this can tell you the right answer, and even if it gets the right answer right most of the time, I really don't feel comfortable with the computer telling me what the right answer is. I need to think about it myself. And also, with all I have learned from the professional forensic tool mark examiners, they told me about stuff I would have never thought to tell the computer to look at. I mean, their experience really does matter. And I don't know how to and I don't think anybody is smart enough to know how to transfer exactly what they're thinking when they say two things do or do not match into a computer. But we're trying as best we can to get there so that we can say, yes, Judge, there is some kind of a recipe that we can make these comparisons, and this is the answer it came out with. The human being also says X, Y, and Z. So now it's to the jury to decide whether or not they want to believe that.
At this point, the computer method has to be peer-reviewed.
Yes, absolutely, absolutely. It should.
Other stuff.
Yeah, like I mean, right now there are a lot of people, and I absolutely pat them on the back. They're trying to make money out of this stuff, which is great. But I'm going to be at court on the other side. If I don't know how their thing works, like with the IBIS, it's not scientific. It doesn't mean anything if I cannot reproduce the results. And if IBIS is doing something to say, well, this is a match, and I can't actually calculate that number. I'm sorry, Integrated Ballistics Identification System, which if you shoot somebody and you leave cartridge cases or bullets around and they're in pretty good shape, chances are the police, especially if it's a high-profile shooting or it's in New York City because they have an IBIS, or a big metropolitan area.
Takeaways: if I shoot somebody, I should take the cartridge cases with me.
I'm not giving you any kind of a, yeah, well, you know, use your intuition. There's different things that you can do. However, yeah, if it goes through the IBIS, and actually the IBIS people do not testify as to the level of how good a match it is based on the number that comes out of their instrument. Mostly because A, they don't want to get into the business of having to go to court all the time. B, they have a proprietary algorithm, which is really a database search algorithm, and they don't want to tell anybody how it works. And C, I don't think those numbers are really that great anyway, that are coming out and making matches and not matches. But it does, one of the things that IBIS is great at when it works, is it is a great aid to the human being to say, why don't you take a look at these possibilities? We're trying to go one step further and say, not only do you want to try to take a look at these possibilities, the computer really thinks these two things do or do not go together. Now, again, and this is where the psychologist can come in, and I would take a step back. Human being, what do you think about what the computer just said? All I'm really interested in is coming up with a recipe and testing how good that recipe is on a machine. Should I replace a human? I don't think it ever will. But I'm still interested in pursuing the problem. So I'm sorry I'm getting off on a tangent of philosophy. But at any rate, you can use R to do this kind of thing, and it's really a lot of fun. And you can, everything that I'm talking about, this is a little hard to reproduce with what I've given you so far, but in principle, if you worked at it enough, it could be done. Or if you want to collaborate with me, I'll just give you everything. And in fact, I think you can get everything on the website anyway, and reproduce this particular graph. And this is not really the way we want to go. We don't want to go up the CCF's route. And I know some of my colleagues, my friends at NIST will see this, and they're going to get very angry at me for saying that, or just telling me, oh, that guy's a crackpot. But they're brilliant. But CCF, cross-correlation, is that the similarity metric we should be using? No, I don't believe so at all. And in fact, if you look at the mathematics of similarity metrics, there are as many as there are stars in the sky. So you can start making arguments, legal arguments too, as to why you're using this instead of not something else. My feeling about it is use as much information as you can to make the best decision you can. And this is just boiling it down to one number. It's not going to scale well on big databases. Maybe I'm wrong, I don't know, but I'm not going to pursue this. So what statistics can we use if we're not going to take a univariate approach? Well, I know I love using mathematics to do things. And one or a couple of areas where that occurs in real life is marketing and item sorting. In other words, there are algorithms out there that take features that characterize an object, and it tries to match those objects to specific categories. And a great example of that is you guys use, anybody in here use, I said this already, you use Amazon? Does it occasionally pair you with things that you kind of like to read? I know it does for me. I like to buy science and statistics books and heavy metal music. And it usually presents pretty good choices to me, and classical stuff too. And I have wasted a lot of extra money on Amazon because it told me some things that I might like to buy. What mathematics is it using to make that match? let's use the same thing. And if it wasn't working well for Amazon, they wouldn't be using it because they would have gone out of business. So let's use the kind of mathematics that is used in industry to match things or pair things, and let's just use it for our particular data set. Now, there's a lot of differences, too, between what Amazon does and the problem that I want to solve, but there's a lot of similarities as well. So let's see if we can use that kind of pattern recognition system to our advantage to pair a piece of evidence with a source that might have created it. And we can even go further and maybe try to put a level of confidence on that quote-unquote match that we make. And by the word match, I don't mean exact match. It matches it's exactly the same features. I just mean it fits into the same category. I've gotten yelled at, rightly so, by a lot of lawyers who say, what do you mean by match? Match doesn't, in my context, in a computational context, does not mean identical match. It means it fits into the same category. So what statistics can we use? Well, we use statistical pattern comparison, or if you want the sexy word for that, you call it machine learning. It's basically using a computer to solve the multivariate equations of statistics in order to pair things together. And it's used all the time in industry. And not only, Amazon and Netflix are the two famous ones, but it's used to sort fish on a fishing boat too. You get a big net full of fish, you have all sorts of things in there, and there's an optical reader that kind of tries to figure out what fish it is and what line it should go to be processing it. It's the same kind of idea that's telling the line how to ship the different fish that are coming out of the net. And so the idea is to measure features that characterize the physical evidence, or for our case, surfaces, metrological surfaces that we get out of some kind of optical or stylus metrology instrument. And we train the algorithm to recognize major differences between the groups of features that we get, while taking into account any natural variation and measurement error that we get between the surfaces. And if you were to visualize this in sort of a very heuristic way, we measure a bunch of features for different tool marks. What I'm using are actually the tool mark surfaces themselves. You can use parameters as well. And what the machine tries to do is say, okay, well, I got a bunch over here and a bunch over here. Tell the machine that these are two distinct sets of features from two different sets of tool marks. Find a function that will separate the two. It figures it does a fit, basically something that looks a lot like a least squares fit, or there's other algorithms out there that do other things. It tries its best to draw a line to separate them as well as it can. Then when you have an unknown, if it falls on this side of the line, you say, it came from the blue tool. If it falls on this side of the line, it came from the red tool. And there's different ways of figuring out where this line should be, or if it even should be aligned. What you always have to do with these methods, because you have to train them on sets that you know and the right answer to, and you have to tell the computer the right answer to, you have to thoroughly test them on sets that you didn't train the computer with. So that's one of the major criticisms of this approach, is that you have to thoroughly test them before you can really use them. But in the process of testing them, you get something else that the courts are asking for: error rates, estimated error rates. And there's lots of different ways that you can estimate those as well. So it's a fun problem to work on. There's a lot of meat here. And whenever you do this, basically we kind of have seen this already. You're working with something that looks like you're feeding something that looks like a spreadsheet into the computer, whether it be a spreadsheet full of parameters or a spreadsheet full of z heights. Now, usually when there's z heights, you don't actually look at it as a spreadsheet because there's just too much information, but really it boils down to the same thing. Here's an example of some of the parameters that we have from the spreadsheet that you have in that little distribution. There's a bunch of RAs and RQs and stuff. Now, in practice, we have not taken the approach to use these as our descriptors of the surface. But every surface is described in a row. So this is a surface, this is a surface, this is a surface, this is a surface. And these are all parameters that happen to correspond to those surfaces. Usually, for us, these are actually z heights. And these are just labels that we give the computer. So when we're training it, it knows, these all came from gun 1, these all came from gun 2, these all came from gun 3, these all came from gun 4. But again, ultimately we have to test it out on sets of features that we didn't feed it. And that's called the data matrix. Now, if you want to, it's always a good idea, especially when you start a set of research, is to kind of understand what the data is sort of trying to tell you. Take it with a grain of salt. I mean, you're probably going to really have to get new data in order to do the analysis, but the data speaks to you. Let it speak to you a little bit, and different visualization methods that you can use in order to look at that data. A lot of times what we do is just 2D plots. We'll plot one variable versus another. This is an example which will be reproduced for you by that visualization plot script that I gave you, where we look at RA versus RQ. One of the things that I want to point out here is look at how as arc A increases, RQ is also increasing linearly. What that's telling you is that if you know RA, you basically know RQ. So RQ is not giving you any extra information. We have found that a lot of the parameters do that. If you just look at the equations, this is the same, the sigmas are all kind of line up with each other. One is not really giving you too much extra information than another is. That's why I wasn't surprised when we saw kind of lousy discrimination when we just used parameter vectors in order to discriminate surfaces. Again, if I was a referee on a paper, I would not reject the paper for presenting that idea, especially if it presented the idea and it really worked very well, like 90% or above correct classification rate. We have not seen this in our experience, and so that's why we haven't pursued this. But I don't know. I mean, that's an open area of research. You can, see if you can actually get good surface discrimination to the point where you can actually identify the tool that created the surface with just these parameters. If you can do that, that'd be great, because you really you'll have actually a commercial, something that you can commercialize pretty quickly, because it doesn't take a lot to calculate these parameters. I just don't think it's possible, especially because if it was possible, it would have been done. You can do pairs plots too with R. So you can plot a whole bunch of variables against each other. This we've found very handy too, as long as you don't have too many variables that you want to look at once. So what this pairs plot is trying to tell you, and you can also reproduce exactly this plot in that script that I gave you, is this plot here is SA versus SQ. This one over here is SSK versus SKU, so the skewness and the kurtosis versus each other. As long as you only have like 5 or 6 variables that you want to do pairs plots between, this is okay. I've accidentally executed this routine on like a 250 by 250 size matrix. You get a mess. You can't see, the plots are like this big. But if you can kind of slice out of that some things that you want to look for, this is a handy tool to use as well. And that's what that visualize with plot script that you've got on your thumb drive. And these are from our real data set as well. I did not calculate the parameters though with R. These were calculated with mountains, and I just dumped them into that spreadsheet. Eventually we'll do this with R, but we haven't yet. And you can also make histograms, and you can make them really pretty. This is like a Z height histogram that you can actually do in mountains no problem. And you can plot many of these things against each other with conditioning on which tool it came from. So of the 5 tools, these are the different Z height histograms. Again, the reason why I put this in is because I wanted you to be able to see how you could do this kind of a plot with the R. So look in that, visualize with plots, and you'll be able to reproduce this kind of thing. So it might be useful to you in your research. You can do probability density, so you could take your histograms and you convert with like one line of code, you can fit them to a density plot. I did not put this in the script though, because this, even though it's a really easy command to execute, it's a really easy command to go very wrong with. It's dangerous to fit densities to histograms. You gotta know what you're doing. So I kind of left this out. Not so much because I don't trust you or anything like that, but I just don't trust I don't want to get yelled at if anybody does anything stupid with it. So I just kind of left this out. You can go figure that out yourself, how to do this. It's really simple to do, and if you Google R density fit histogram, the command will come up to do this. Yep?
When would you want to use against plots?
Sometimes you might want to do a numerical, a little bit better than just a straight off integral based on the area of the bars that you get in the histogram. So you might want to fit a density to it. Other things that you might want to do are calculate specific probabilities, and the best way to do that is to do integration, and it's best to have a actual density. With our simulation, we ended up having to fit densities to histograms so we can sample out of those densities. So it depends on the algorithm and what you're trying to accomplish, but sometimes it's handy to have these things around. Just be careful with them because they are very variable depending on the parameters of the fit parameters that you feed into them. And it's not always a best choice, but between different choices, you do get very different fits. So these things can kind of be dangerous.
are you trying to predict between points like interpolate?
Am I trying to? Oh, yeah. No, not here, but that is something you could do with this kind of a feature. And if you want to do interpolation between points, R, and also MATLAB, but R has full interpolation facilities, so you don't have to rewrite all that stuff yourself. You can do interpolation, no problem. And yes, I could see how you could come up with an interpolation algorithm with this kind of an idea. Just be careful with fitting densities to histograms. It's messy. You could also do these cumulative density plots, which you guys like to. Who's a surface metrologist? Who's an engineer in this room? You guys in the back. You guys like to call them Abbott Firestone curves. No? You know what an Abbott Firestone curve is? Anyone? Anyone? No? Oh, in mountains, you can produce this thing called the Abbott Firestone curve, and it sounded really fancy. I thought it had something to do with tires when I first started looking at this stuff. It is what the Abbott Firestone curve, and they tell you this right in the help. The Abbott Firestone curve in mountains and in the literature is just a cumulative. If you take your histogram and you calculate the cumulative density according to that histogram and you turn it 90 degrees, that's what mountains calls the Abbott Firestone curve. It's a cumulative density of a histogram. And that's all I've done here. This I don't think I put in the script because it was kind of getting time to go to Massachusetts, so I didn't type this in. It is relatively straightforward to do. Get comfortable with the program first, and once you're comfortable with the program, if you can't figure out how to do this, either you could look it up in a book or ask me or ask somebody else. This is not very difficult to do. Okay, so we talked a little bit about getting your data into R and then making various kinds of 2D plots for it. The ones that I find most handy are just plotting one variable against another to see if there's some kind of relationship there. Like plotting the surface parameters against each other just to see if there's a kind of relationship. And usually there's a very strong, with surface parameters, usually a very strong relationship, meaning that one surface parameter doesn't give you very much more information than another surface parameter. If you know one, you really have a functional relationship to the other. And we talked a little bit about plotting histograms and plotting densities, and just be a little bit careful if you do fit non-parametric densities to histograms. It can be real fishy. So what I want to start to do now is get into a little bit more of the multivariate statistics stuff. This is over at 5:15, right? Is that right?
No, before 5 o'clock.
Oh, before 5 o'clock. Okay, so I got a couple more minutes to bore you, and then once I have finished boring you with PCA and SVM, we'll forget about the error rate stuff at the end, and we'll go back to those scripts. I'll talk a little bit more about how to execute them. Before I do that, though, I want to get into your head what principal component analysis is, because it is such a ubiquitous tool in multivariate statistics. It has many, many different names. It was first, I think, I might be wrong about this, but I think the first person to come up with it for statistics was this fellow named Hotelling, who came up with a lot of multivariate statistical stuff in the 20s and the 30s. It is a technique that has been around for at least 100 years. It's really nothing, I mean, you need a computer to do it, but it's really nothing fancy. And in fact, is anybody in here from physics or have a physics background, or did you ever do anything like diagonalize a matrix? It's diagonalizing a matrix. All it is you put together a covariance matrix, which takes one line of code in R and SPSS and everything else. And you diagonalize it to get out the eigenvectors and the eigenvalues. Those are your PCs. But a little bit more theory. They are latent variables. Latent variables in statistics are weighted combinations of experimental variables to synthesize a new variable. People love to put all sorts of physical ideas as to what a latent variable is trying to tell you. The shrinks, the psychiatrists, no, I'm sorry, the psychologists love doing this. Psychometrics is built around the idea of largely trying to interpret latent vectors. Do they really mean anything or not? Like IQ is a latent vector. It's like something that's trying to attribute intelligence to a bunch of different variables that you can actually measure in the lab. Is it really physical? Yeah. My personal uneducated feeling about it is no. And I extend that to surface metrology and quantum mechanics as well, where you also see these things. Latent variables are convenient mathematical devices and really shouldn't be read into more than that. Maybe there's a physical interpretation from them, but if there is, you got lucky. basically what you do with PCA is you calculate these linear combinations of things that you actually measure in the lab. In other words, a weighted average. And from them you can get these things called scores, which are also referred to in the literature and statistics as components and factors. And the weights themselves that make up these latent variables are called loadings. So if you ever see the word loadings in a statistics book, this is what they're talking about. They're talking about basically the weights that you multiply the physical measurements in the lab by in order to, when you string them together with sums, to get your latent variable. And again, this is something that people love to put physical intuition behind. Sometimes there is, sometimes there's not. I really just try to ignore it. And most latent variables that we study are very simple to calculate, linear combinations between experimental variables and loadings, and it boils down to it. And remember from physics, the dot product. If you take a bunch of numbers that you measure in the lab and you dot it onto your loadings, you will get a score that it represents. And people love to put interpretation on these and some kind of physical interpretation on these. And I personally feel that the only thing you can put a physical interpretation on is something that you observe in the laboratory, which is that. That's what you measure. The rest is just mathematics. That's it. And actually pretty simple mathematics. At any rate, it can be used as a nice device to take data and compress it down, but not to the point where you've lost tons and tons and tons and tons and tons of information. And principal components analysis is the major way to do that. It's probably the major way because it's been around forever. People understand it pretty well. It's in lots of other fields under different names. It's matrix diagonalization. And it tends to work well in a lot of applications to summarize a multivariate high-dimensional data set. The way it works in 2 dimensions is this. So I'm going to describe this in 2 dimensions, and you can make analogies in your head with 3 and 4 and 5 dimensions. And by a dimension, I mean the number of measurements that I use to characterize something. So for example, for this piano, I might characterize it by its weight, its length, its height, maybe, I don't know, what's different about it? The company that makes it. So a bunch of different attributes can be strung together in a vector to describe this guy. I would, in other words, describe them as a high-dimensional feature vector. Especially if it's more than 3 attributes, I can't visualize it in space anymore. I can't visualize 4 and 5 and 6 dimensions. PCA is handy for taking all those dimensions that you measure and, according to the PCA criteria, summarize it as well as possible with less numbers. Those numbers don't really have a physical interpretation anymore, but they do summarize the same information. So if I was to do this in 2 dimensions, let's say I measure height and, I don't know, weight of the piano. So 2 different numbers characterized as piano. And if I plotted them against each other, let's say I get a plot like this. If I was to do 2D PCA on this, what it will do is it looks for direction, or the summary of data or summary of information in PCA tells me which directions in space does most of the spread of the data occur. If I was to do 2D PCA on this, just looking at it, I can see I got a lot of spread this way. And because of the way PCA works, when it looks for the second dimension of spread, in other words, the second most largest spread, direction of spread in the data, it would have to be orthogonal to it or at right angles. So I could see just by looking at the data, most of the data is going this way, and then where would you think that the other direction, the other PCA should be pointed? Would it be pointed out at you? Would it be pointed over here? Would it be pointed over here maybe? So one is going this way. That's the largest amount of spread. And direction is second largest amount of spread, just kind of eyeballing this. If I had to pick a direction that's at right angles to the first direction, I would say this direction. There's also a lot of spread as well. Not nearly as much as the first direction, but if I had to pick a dimension that's at right angles to the second, that's what I would pick. So running 2D PCA or running PCA on this, that would be the vector that represents the first PC, and that would be the vector that represents the second PC. And what I have done with the blue arrows is, the fancy way of stating that is to say I have plotted the data in the basis of my first 2 experimental variables. In other words, the the numbers that describe this arrow and this arrow are my experimental basis set. I plot the data with respect to them. There's no reason. These are two arrows too. I could plot the data with respect to these two arrows as well. So if I did that, if I plot the data with respect to these two guys, I then plot the data with respect to the principal component basis. Doing that, what do you think is going to happen to the picture if I go from this basis to this basis? Yep, it rotates it. So if I use this as my coordinate axes instead of this as my coordinate axes, actually nothing has changed about my data other than I've rotated it around in space. That's what matrix diagonalization does for you. It just rotates your data. It's probably doing it in a very high dimensional space, so you can't make this picture. However, in 2 dimensions, we can make this picture. And while this and this might have been physical quantities that I could actually measure in a lab and understand, these and these aren't necessarily. They're just principal components, and that's it. The advantage of doing this is that look at the length of this arrow. If I was to throw, so each of these points is characterized by 2 coordinates. If I was to throw away that coordinate, I still, just kind of looking at this, I still would get an overall sense of what the data looks like in space. So by throwing away this second PC, I'm not really throwing away all that much information. And I have compressed the information in the data set down to a lower dimensional space. In other words, 1 dimension instead of 2. That's what PCA does for you. You throw away the small arrows that are produced by PCA. You've actually gotten rid of some dimensionality to the data set. If you can throw away all but 2 or 3 PCs, you can make a 2 or 3 dimensional picture of the data. Now again, in order to do that, you are throwing away information. The hope is, though, that the amount of information that you're throwing away isn't very much. In other words, the length of the PC arrows aren't that big. The length of the PC arrows does have a measurement that does get spit out of the computer programs. It's called the variance. So the variance of each of the PCs is something that always gets spit out of the programs. And you can say, okay, well, this variance isn't very big, so if I threw it away, or if I threw away that PC, I'm not really throwing away a lot of information. Now again, this is a little bit of a cheat, because even if I am throwing away a lot of information, I usually do look at the 2 or 3D plot. But the point is that you use PCA kind of hoping that you're not throwing away a lot of information by summarizing the data. PCA is often, though, used as a way to get rid of noise in the data set. If you throw away the lowest variance PCs, it is thought that with a lot of data sets, you're really only tossing noise. You got to be careful, though, because we've come across a couple of data sets where we did do that, and we actually got lousy discrimination. It wasn't because we were throwing away noise. We were throwing away subtle differences between the data sets. So you got to be a little careful with using PCA along that philosophical line. One of the reasons why I do like PCA, though, is I'm a visual person. I like to have, even if it's not a great picture, I still like to have some picture of the data in my head. And I can't visualize 18 dimensions, but I can visualize 2 or 3. And I usually will look at my 2D or my 3D PCA just to see what it looks like, even if it might not be a very accurate picture. And yeah, you could, some people beg to differ with me about doing that, but I like to do it.
One of the issues with doing this is that if your measurement aligns with a controlled variable, if you're doing experiment, and sometimes you're doing things over the course of time. This is a time series. Then
don't do this.
Then you don't do this.
Yes.
And the other one that I've seen where this kind of approach can implode is if you've got a shotgun blast and 1 point out here, you get a very large effective coefficient of variation for that one large moment arm data point. If you have an abnormal data set where you've got a shotgun blast and a point over here, you're going to find that is the primary component of variation.
So yeah, I think the way the multivariate statistics people would say, the word that I know for that, and I think this is what you're talking about, is there's a lot of leverage to that data point.
Right.
yeah, that would run into problems too. And as emphatic as I might be about R and anything and any of these techniques, it's only for it's for show. Yeah, with anything that I talk about in here, you have to be very, very careful. And you're absolutely right that there's a couple. This is not going to solve your problems all the time. In fact, it can really lead you down a wrong path. I'm just want to show you that this stuff is out there and that anybody in this room could reproduce anything that I'm talking about if you really want to get into it. But don't start, don't take it into court. Definitely don't start publishing papers with it until you play. Yeah, absolutely.
Things, objects.
Yeah. Yep. There are ways of playing around with that I didn't bring that talk with me. But if you want to have me back to whatever, I could talk about fishing out outliers too and how those outliers might affect your PC. We can talk about that as well. Yeah, be careful with this stuff though. It can lead you very astray very quickly. Anyway, that's how PCA works. Is really the take-home message here is it's really just rotating data around in space and to plot it in a different basis. And by throwing away some of those basis vectors, and hopefully not throwing away too much information, and you're summarizing your data well. Although, again, you can run into some problems doing that, depending on your data set.
Does it help with differentiation?
Does it help you with what? It might, but it's not ab initio meant to do that. It might reveal differentiation, especially in a 2D or a 3D plot. However, PCA in and of itself doesn't look for differentiation. I'll tell you right now, if you do, and I see this in, like, I quite often nowadays will publish in Journal of Forensic Sciences, and PCA is something that's sexy to do in forensic science right now, and people are plotting these, are publishing these 2D and 3D, or actually mostly 2D PCA plots, where they show you this crisp discrimination between different, let's say, data sets of evidence. If you can see differentiation in 2D or 3D, you probably could just look at whatever it's like the difference between, I don't know, me and my mom. If you do PCA on my face and you do PCA on my mom's face, lo and behold, you can tell the difference between us with only 2 PCs, even though it might be millions of points that make up our face. So usually if you can see the difference in 2 or 3 dimensions, it's probably not worthwhile doing the PCA. PCA doesn't look for differences for you. It might reveal them, but again, if it's to the point where you can actually visualize them with these kinds of plots, you probably just look at your data set and be like, oh yeah, they don't look anything alike. So you don't, again, you'd be killing a fly with an elephant gun. You don't really need to do that. There are techniques that will do that for you, but again, they have their own sets of problems. Canonical variate analysis is one of them, which I won't talk about. All right. So it's an eigenvalue problem. I'm just going to skip this slide, but if you're from quantum mechanics, you've dealt with this before because this is how you solve a Schrodinger equation. Schrodinger equation in matrix form is eigenvalue problem. So I put this up because I went back to my old research group to give a talk to say, what are you doing now? And so I wanted to say, look, I'm really not doing anything different. And that's why that was there. So if you're really into matrix algebra, that's really what's going on with PCA. It's just a simple eigenvalue problem. All right. Back to tools and tool marks and surfaces. So these are 2 tool mark surfaces, which have been cleaned up a little bit to get rid of some noise. And I think I filtered them a little bit too. I just wanted to show them as examples. And over here I have mean profiles overlaid by I believe these are screwdrivers. Same screwdriver made all these different surfaces that I boiled down into mean profiles, and I just overlaid them all on top of each other. And same thing over here. And this is kind of like what you were talking about before upstairs at coffee. So the actual information that I am feeding into R is I get this out of the microscope. I clean it up a little bit with some of the digital, either the Zeiss, whatever my microscope software is, or whatever mountain software is. And I boil it down into a mean profile. These are what I actually feed into. After I remove form, I feed these into R. That's another problem with surface metrology, though, I really think, is what's form? I don't know. I have one definition. I usually remove a third order polynomial. Somebody else who was talking today about hip joints, he has a totally different and much more operational concept of what form is for his particular data set. So that's something that I think a bridge that surface metrologists really still have to cross is let's nail down what do you mean by form a little bit more. I think it's very application dependent. Am I totally wrong in saying this? I don't know. You guys know a lot more about that than I do.
That's absolutely true. I mean, there's some... Yeah.
There's multiple contexts for form.
Yeah.
I mean, in surface metrology, it's what is not the straight line.
Mm-hmm. Oh, okay. Well, that's a little bit better than the picture I had in my head. At least I have a function I can think about now. So if it deviates from a straight line, and what kind of slope?
Frequencies.
Okay. How do you define the frequency band?
So there's a upper and a lower frequency content. Mm-hmm. Okay, and it's codified in the standards.
So you should separate waviness and roughness before you remove form?
No,
or
you do.
When you remove the waviness, you've taken out the form.
When you remove waviness, okay, so then what I was calling waviness is probably not what you would be calling waviness. You would probably be you would call this roughness. Would you call that roughness or would you call that waviness?
No, you have no units, so I'm not going to call it anything.
Ah, okay, so that, all right, I have to talk to you some more.
Because it looks smoother than what you started with, I would call it waviness.
That's kind of what I do too, but now I know a little bit better how I should make my plots. I got to talk to you guys some more because I have a really big problem with these definitions and nailing down exactly what you mean. But yeah, okay, you gave me some ideas, so I need to look at straight lines. But this is a good tutorial for me.
Well, the screwdriver has an inherently straight line, but you may have, there's cylindrical surfaces where the form should be cylindric.
So yes and no, right? I mean, you have a geometric specification for form, which should not be a straight line, it should be a curve.
Yeah.
Right? But when you do the math to extract the roughness, okay, you can remove the form and leave yourself with a straight line. Yeah. Right. Now, whether you're going to do it based on flattening it out and doing the math, or whether you're going to do it based on, keeping it wrapped around the curve, but looking at the deviation from the curve, 6 of one, half a dozen of the other.
Okay. I have to talk to you two more. Okay.
Ideally, a screwdriver is straight. I agree with you. Yes.
Okay.
Or wedged, anyway.
Well, yeah, I have nothing to say other than I probably should run some of this stuff past you first before I go out and say this is how you should do things. But anyway, I've gotten to this point with my surfaces, so hopefully it's okay. And now I'm going to take those. What I see here is signal, and I can use signal processing tools on it in order to make comparisons. So in fact, I've kind of taken in the codes. If you ever see the word signal in any of my comments, I'm talking about something like this.
For things like screwdrivers and the cartridge casings and things like that, what I would personally do is I would take out the best fit straight line or the best fit plane, because that is an artifact of how you mount it inside your microscope.
We have also, yes, that is true, but I have also seen things in there that I know they're polynomial in shape, whether or not it's two-dimensional. Well, I could tell the difference between even and odd dimensions. I will usually kind of, even if we get a little bit, I'm looking for a beautiful, straight set of lines that I can see in my picture. And I will take out usually up to third order polynomial in order to get the sharpest set of lines I can get. I can usually get a little bit sharper if I go to 5 or 6 or 7 dimensions, but I stop at 3 in that, well, I don't want to overfit.
I get uncomfortable with that because when you take out stuff, you're taking out data.
Yes, that is true. This is true. But I can't see my lines that I can't see the lines in the Z heights that I can in the picture. I see in the picture there's definitely some, whatever's happening up here on the surface is happening down here. It's just so subtle.
You've got noise which the math doesn't pick up.
I wouldn't say it's noise because noise is localized. This is over a long distance. Maybe I'm pulling out information that is a part of the tool surface, but
Your eye picks contrast really well. The human eye is very good at picking up edges, and the tool that you are using is not necessarily good at picking up edges. The mathematical tool that you are using to process is not necessarily good at picking up edges. And I don't want to suggest, but I'm going to throw out the word differentiation at you.
I don't want to suggest. Wait, so can you say that again? I didn't quite understand.
You never heard me say this word, differentiation.
Okay. So I don't want to put in more differentiation that really exists in the surface.
Differentiation is one of the operators which enhances edges.
Okay, but when you fit a, well, we'll talk about this later.
Yes.
Yeah.
That's good over a beer or something. Yes.
Also, there was a talk about hue transforms. The hue transform.
There's other kinds of transforms, and absolutely. If you do Fourier or other kinds of stuff, edges have higher frequency content, and maybe that's the kind of filtering that you want to be thinking about as opposed to being polynomial removal. It may be a spatial frequency content.
Okay.
Kind of thing.
Yeah, I wish I had you in my lab so I could show you exactly. Well, yes, let's exchange information later. At any rate, I have a mean profile, which looks like a signal.
Yeah, absolutely.
And each of these is just really, as far as the computer is concerned, a list of numbers. So I know I've given this talk a couple of times, or versions of this talk a couple of times, where people came up to me afterwards and said, "What data are you using?" And this is, I want to nail down what I'm using. So each data point is a height on this surface. So each of these is a different data point. And so each of these makes up a row in my data matrix. Every row in my data matrix is a different z height. So this data matrix can get pretty big pretty quickly, but there is a lot of dependent information in it. That's why I use PCA on it. In other words, each of my profiles is anywhere from 4,000 to sometimes I get to 8,000 points long or so, depending on how much real estate we decide to record with the microscope. And I should have put a scale in there, and I didn't.
If you plotted your matrix using a mesh 3D command or something in MATLAB or something like that, you would wind up with actually something like what you see.
Yes, exactly. You would see the data matrix. Yes, exactly. And and it's a very highly redundant representation of information, because whatever's happening over here is very closely related to what's ever happening over here and here and here. That's what PCA is meant to do. It's meant to take out that redundancy by reformulating your data set in terms of these synthetic variables. So instead of plotting the data with 8,000, or instead of representing the data with 8,000 dimensions, I can represent it with usually, it depends on the data set, but a lot of times 45 to 50 PC dimensions will give us good discrimination when we run it through a discrimination algorithm. But PCA will allow us to summarize this very big data set with a lot fewer numbers than what is actually physically make up this signal. So that's why we use PCA. We use it as a data compression device. Again, you are changing the data set and throwing things away that way, but in a way that at least I know is used in a lot of other fields to good effect. And ultimately, we're after an error rate. So if I know the right answer, the computer doesn't. If I train it up after I've done all this math to it, if I train it up, I still get the right answer 99% of the time. Right. Even if I have changed the data set, I know I'm doing a good job, and I have a discriminatory algorithm.
You want to be able to do this in a computationally efficient fashion, so that you're not
yes, exactly.
If you have 27,000 lists to compare, you're not.
Yep, exactly. And so this is just a quick. This is produced in R with RGL. This is if we took a bunch of real data, a bunch of real profiles, and simulated a bunch more. Ultimately, I think we ended up with about 1,700 profiles or so. If we take all of those and then project it into three-dimensional PCA space, we get a picture that looks like this, which doesn't look that great, except the fact that I've thrown away a lot of information in order to get to 3 dimensions. And really what I look for here is just, is there qualitative differences, or am I seeing some qualitative differences between the different tools? And I already am seeing clusters, even though I've thrown away more than 50% of the information in the data set. So we can get at least some kind of a visual picture with 3D, with really super reduced PCA. to do the discrimination, I don't do it on 3 dimensions. I add a lot more dimensionality, which begs the question, how many PCs should you use? In other words, how far down in PCA space should you go before you really should say, I'm throwing away too much information? That's model fitting, is what that is. In order to do that, you need a discrimination algorithm, because what PCA won't do for you, and I'm going a little faster now because we're running out of time, so I apologize, but what PCA does not do for you is it doesn't say this point belongs with this particular data set. All it does is summarize information, and that's it. You need to use a discrimination algorithm on your data set in order to make decisions about it. One that I use a lot is support vector machines. Another kind that a lot of people use in industry are neural nets. In fact, they're used to sort the mail. You have an optical character recognition routine, I think developed by a guy at who's currently at NYU, Jan LeCun, in order to separate different versions of 0s and 9s and 8s, so it can separate things by area code. Another kind is canonical variate analysis. There are as many discrimination algorithms, again, as there are stars in the sky. SVMs, I know, tend to work pretty well. They're computationally intensive, but they're reasonably well behaved without having to adjust a lot of parameters. So that's why we use them. So we'll boil our data down with principal component analysis into its essential features, and then we will discriminate different groups in that data by training an SVM. And then what an SVM really does is it looks for, I tell it that these two things are different groups, and it looks for, okay, where can I draw a line that gives me the widest margin of separation? So if I was to do SVM on these 2 different data sets, it would say, this guy and this guy and this guy define the widest gap of separation between those 2 groups in my actual support vector machine, which is just a fancy way of saying a line, is a line that goes right down the middle of that widest gap possible. That's why SVMs tend to work pretty well, because they look for wide gaps between different data sets. But again, you have to test them very thoroughly, because I found that wide gap by telling it, okay, these are all pluses and these are all circles. So I got to test it out on some pluses and circles that I don't tell it are pluses and circles, which is where the error rate stuff comes in, which would be on the next set of slides. So if you're this is all of the math behind it. It's a quadratic optimization problem. Everything I'm telling you is doable in R. You can do any one of these things in R. You can play around with these things called kernel functions in support vector machines to your heart's content and get all sorts of crazy stuff to work for you. This is all doable by the users in the audience. I'm not going to go into the details, but if you want any more information, Google it, look it up in papers, read books, and I'm happy to collaborate as well, although I am slow on email. And again, whenever you do this, you have to be very careful. Read a lot about error rate testing and testing your fit models. And that's what I would talk about next. Let me just give you some words to look up or words to study about. If you want to test your model, a couple of good things to do are cross-validation. In particular, hold one out cross-validation. That's probably the most common thing to do, and it's also pretty straightforward to do it. Bootstrapping, which is invented by a very like one of my statistical heroes, Bradley Efron at Stanford. If you Google Brad Efron, his website, he's still alive. He's getting old, but he's still alive. His website comes right up. He is just a brilliant, brilliant writer. He is amazing at taking very complicated concepts and explaining them to anybody. And he's a guy who came up with bootstrapping. And it's you'd never in a million years think this would work very well, but it's a really good way to test out your discrimination algorithms based on having relatively limited sample size. So I highly recommend you go to Brad Efron's website and read some of this stuff. Again, he's mostly working on empirical based things right now, but he was the inventor of bootstrapping. He always regresses back to bootstrapping and everything that he does. And he is just an absolutely brilliant writer. I love reading his work. And then the best thing to do probably is I'm kind of, it doesn't appear so, but I am practical. Test your data, build your model on as small a training set as you can get away with, and test it out on as big a test set as you can get away with. We're not there. Big test sets are not in existence with the exception of DNA profiling in forensic science. We're still building up to that point. Eventually we'll get there. In industry, they're actually starting to, and a lot of spots in academia, they're starting to talk about big data, especially in genomics, where they have tons and tons of numbers that they can look at. We're not here we're not big data sets in forensic science. In order to get to this, I have to do simulations still. But that's probably the best thing. That's the model that I believe the most. If I do a 90-10 split, 10% I train, 90% I test. If I get a 99 or 99.9% correct classification rate, I know I can tell the difference between these patterns. And another good thing about bootstrapping is it also gives you confidence intervals around your error rate, which is better than a point estimate, which is what you'll get with a cross-validation. The statisticians really like interval estimates if you can get them. So instead of just quoting one number for your statistic, give me some level of uncertainty as well, which is what the confidence interval will give you. And there's other things that you can do, like conformal prediction and other things that empirical Bayes, like Brad Efron is talking about now. If you're interested in any of this stuff, feel free to, we can talk over beer. I like beer. I'm going to ask you, is there any questions? I'm sorry, I really went through that last stuff really fast, but is there any questions? What I want you to know is you can do PCA with R, no problem. It's really not a sophisticated method at all. It's a matrix diagonalization. You can do support vector machines with R, no problem. And we have found them very useful in practice to discriminate between different tool marks, using the actual tool mark or something related to it, like the mean profile, as the feature vector. Just boiled down a little bit with PCA. And there are as many discrimination algorithms as there are stars in the sky. You may find that something else works a lot better for you, like nearest neighbors or canonical variates or a bunch of other things. You may find that you are able to do discrimination based on parameters themselves. We have preliminarily found that they don't really work that well for fine-tuned surface discrimination, but maybe they really do. I don't know. And that's what I have to say about that. If you want any of the data, it's available on the website. Hopefully it'll be up and running by the time I get home. If you want any help with those R programs, so to get you up and running, I'm happy to. I'm going to be around till Wednesday morning. So feel free to talk to me. I can easily bribe with beer. And if you want to talk about any of this error rate stuff, which I really did not hit very much at all, I'm happy to talk about it. But this is also real research level stuff where I don't know if these are right. I mean, I'm just kind of starting to put this. We haven't published any of this yet. I'm just starting to put it out there to say, hey, what do you think? Beat me up. And people have been happy to beat me up. So anyway, thank you very much. Any questions? Okay, goodbye.
Thank you.
No problem.